necessarily increased from transmitter to receiver. So the indistinguishability problem leads to the following kind of distortion. So let's say this is our transmitted waveform. So every t seconds we add a 10 to 1 or a 0. So the 1 means we release a microtubule, the 0 means we do nothing. The problem is the 1s can arrive out of order. So for instance, let's say that first one is delayed into the second time instant. Then my receiver will see this. It'll see that 1 arrive over here. A 0 means do nothing, so a 0 is not really affected by delay in any way. This one might be delayed, let's say 2 time instants, so that'll arrive all the way over here. Then this one, let's say that this one is delayed only 1 time instant, so that arrives on top of this one. So now we actually observe 2 microtubules arrive during that 1 interval. This one, let's say, is again delayed 2 time instants, so it arrives over here. And this one, let's say, is not delayed at all and arrives in the same interval in which it was transmitted. So basically what you have is a huge permutation. And not just a permutation, but a permutation in which objects can collide, as they did here. So your job as the receiver is to take this weird permutation with all these collisions and try to figure out what was transmitted. So this is not a trivial job. What we've done in this work is we've observed that, in fact, mathematically this can be described by a Markov chain. So this receiver here could only have come from transmissions basically governed by that arrival time PDF. Because that's limited in time, this arrival can only have come from, let's say, transmissions here, here, or here. So within the last 2 time instants. So that's basically a Markov chain, so this is only dependent on transmissions within the previous, let's say, 3 transmissions. That's not exactly true, that's an approximation, but information theoretically, as we show in the paper, that leads to a lower bound on the achievable rates. So here are some of our results. What I'm showing you here is the mutual information, which is the highest possible rate of transmission of reliable information, plotted with respect to this is px, so that's the probability of sending a microtubule. That's the probability of basically generating a 1 in any instant. So basically over here, 1s are extremely sparse. Over here, they're much more dense. So basically, our first point here, which is at px equals 0.5, that basically means 1 out of every 20 transmission intervals contains a microtubule. So our observation is this. The time rate of communication is quite low. This is in bits per second on the vertical axis. So the maximum, so let's take a look at this, which is for a 10 micrometer channel. It tops out at about 0.4 bits per second. For 20 and 30, it turns out it's not much different. These max out at about 0.35 bits per second. So one way to interpret this is to say, if you have a decision that requires 1 bit, so for instance, let's say that decision is direct the chemical reaction towards this sensor or towards this sensor, you basically need 3 seconds to accumulate enough information to make 1 reliable bit of decision. So in other words, in order to communicate that decision from the length, from one end of that channel to the other, you basically need 3 seconds to do it accurately, at least 3 seconds. Alternatively, the information rate in terms of, that should be microtubule, the information rate per microtubule is quite high. So over here, we have, let's say, just a little over 0.1 bits per second, but I'm transmitting 0.05 microtubules per second. So if you work out the units, it turns out that that's more than 2 bits per microtubule. So your bang for your buck per microtubule is actually quite high. we're not surprised by the fact that the time rate of communication is quite low, because the propagation speed in this channel is quite low. Nonetheless, 3 seconds per bit. Although I mean, it sounds, you're not going to transmit an MP3 over these kinds of channels, but I mean, decision speeds of minutes are acceptable in lab-on-chip environments, so we don't feel that these low bit rates impose any huge burden. So this concludes my talk. I'd like to acknowledge assistance from Satoshi Hayama and Yuki Moritani of NTT Docomo, who introduced me to this problem. And if you would like any more information, there's my contacts. Are there any questions? Yes?
The results that you show, are they all results from simulations, or is there any analytic theory? I mean, it sounds like a diffusion drift problem, which can be solved by Fokker-Planck equations. So did you do any attempts in that direction?
So what we're trying to get is we're trying to get the mutual information. The mutual information, it can be written as an expectation in terms of the probability of the inputs given, the probability of the outputs given the inputs. We can write down the exact equation for the probability of the outputs given the inputs. What we can't do is we can't evaluate in closed form the expectation over that probability that's required in order to calculate the mutual information. I deliberately excluded all of the mathematics here because I'm not sure it would be relevant to this audience. But certainly we can discuss that offline. In the end, what happens is that the expectation that's required in calculating the mutual information, we do that as a Monte Carlo expectation. So in other words, we're basically simulating in order to calculate.
Right, because I guess it follows directly from the probability distribution function, which can be solved with Fokker-Planck.
That's correct. So we can, yes, so you can write down the probability, the first arrival time distribution. That can definitely be done theoretically. Steps beyond that, we've chosen to do that in terms of Monte Carlo simulation. I'm not going to say whether or not I think that there's any closed form solutions that can occur there. I suspect not, but that's not a direction that we've gone. Yes.
You show that there's the receiver need to guess what the transmitted data is.
Yes.
Would you be able to guess 100% correctly or with some other lane?
So the physical meaning of mutual information, which is what we're calculating here, is that there exists an error-correcting code such that there exists an error-correcting code with that bit rate such that reliable communication with 100% accuracy is possible. So in other words, if you do some fairly sophisticated signal processing, it is possible to eliminate all of the errors at that bit rate and at no higher bit rate. Now, in practice, what these results mean, they're a fairly loose upper bound on what you can do. So it's very likely that we can't implement very, very complicated error-correcting codes in these kinds of environments. So what that implies is that the bit rates that I'm showing you are a loose upper bound on what you can accurately do, and you will be unlikely to be able to eliminate all of the possible sources of error. So that's what we see in practice. So in the analogy to electrical communication is in the Gaussian channel. We know that if you're transmitting uncoded information, in other words, without an error-correcting code, the Shannon limit, which is given by the mutual information, is a very loose upper bound on what you can do. So you actually need to transmit either much more energy, or you need to tolerate much more errors in order to as opposed to what the mutual information was telling. Any other questions?